Hi everyone, welcome to the Arithmetic Zone. This is part 4 in our series on the unit circle. So we've covered a lot in our journey through the unit circle, from part 1, learning about the special right triangles, to part 2, building the unit circle itself, understanding radians, to part 3, where we covered some basic trigonometry and saw the different relationships with trigonometry in the unit circle. And in part 4, sorry, which should be the final part, we're gonna build off upon what we talked about in part 3 of trigonometry, with the ultimate goal of graphing the sine, cosine, and tangent functions. So let's get started. So we have this technique called all students take calculus, which is really just a way to memorize when sine, cosine, and tangent are negative and positive. In part 3, we really only worked with the trig functions in the first quadrant because all of the trig functions are positive in the first quadrant, no matter what. And that made life easy when we were first getting accustomed to these new trig functions that you may not have seen since a geometry class. But when we go further into the unit circle and trigonometry, we have to account for the fact that the different quadrants exist, and these functions will take on different properties depending on the quadrant that they're in. So we have all students take calculus, and it's really just an acronym to remember this pattern. The A goes to quadrant 1, the S goes to quadrant 2, the T goes to quadrant 3, and the C goes to quadrant 4. And if we remember our definitions of sine and cosine, we should remember that sine is associated with the y coordinate point. Cosine is associated with the x coordinate point. In tangent, there wasn't a rule, like a definition of tangent, but we should know that tangent is the ratio of sine and cosine. So this A in quadrant 1, it's really just gonna be our placeholder for all. All of the trig functions are positive in quadrant 1, which makes our life really easy. Sine is positive, cosine is positive, tangent is positive. And if you learn about the reciprocal trig functions such as secant, cosecant, cotangent, they're also all positive in quadrant 1. I won't be going over those reciprocal trigonometry functions in this unit circle series, maybe in a different video, but they are worth learning if you do want to take some time to research that on your own. So this, in quadrant 2, we have the S, and that's going to stand for sine, and that's going to indicate to us that sine is going to be positive in quadrant 2, and while cosine and tangent are going to be negative. And if we remember our definition of sine being the y coordinate, it makes sense why sine is positive in quadrant 2, because our x is negative and our y is positive here. So cosine is going to be negative if it's our x, and sine is going to be positive if it's our y. And obviously, a negative divided by a positive number will yield a negative number, which is why tangent is also negative in quadrant 2. Now with quadrant 3, this t is going to be tangent. Tangent is going to be positive in quadrant 3, whereas sine and cosine are not, because in quadrant 3, it's negative, negative, and the ratio of two negative numbers is going to be positive. Now in quadrant 4, as you may guess, the C is for cosine, because in quadrant 4, cosine is positive, whereas sine and tangent are negative, because here it's positive, negative. So our x is going to be positive, cosine is positive, the y is negative, sine is negative, and tangent is going to be negative because it's a positive, or rather it's a negative divided by a positive number. So we have that locked in place. But if we look at our unit circle, actually, we see all of these angles, and it can be really overwhelming. And we have to have a definitive way to traverse through this unit circle in an efficient, practical manner. And that's why all of these angles in our quadrant 1 are super important, because using these angles, we can easily derive all of the rest of these angles without having to memorize the unit circle. So if you have some unknown angle theta, You can use these reference angle calculations in the table below. This is in degrees, by the way. We will cover how to do this in radians in a little bit. But you can use these short little reference angle calculations to pinpoint which reference angle corresponds to the angle that you are dealing with in the current problem or moment. So in quadrant one, you can see that the angle calculation is theta. If you're in quadrant one, you are at the reference angle. 30 is a reference angle, 0 is a reference angle, 60 is a reference angle, etc. But if you're in quadrant two, you can use the formula 180 minus theta. So let's say we have the angle, let's say theta is equal to 150. We can use 180 minus theta, which is 150, to get 30. So let me just add these little degree signs. The 150 directly corresponds to the 30 degrees. That's our reference angle. And at 30 degrees, we know that the sine of 30, or our y coordinate, is equal to 1/2. And cosine of 30 is equal to the square root of 3/2. So let's say we wanted to take sine of 150. Well, we know that sine, or rather, we know that 150 is in quadrant two. And we've already established through our all students take calculus technique that in quadrant two, sine is positive. So it's going to have the same exact value as in quadrant one, 1/2. So that makes that easy. But sine, or rather cosine of 150, cosine is negative in quadrant two. This is actually going to be negative root 3/2. It's going to have the same value, but it's going to be negative. And we can verify. If we go to our unit circle, we pinpoint 150. Yes, right here. This is our x. This is our y. So cosine corresponds with our x, sine with our y. Cosine of 150 should be negative root 3/2. That's what we have. And sine of 150 should just be 1/2. And that's what we have. And this holds true for any of the angles in quadrant two. And the same can be said in quadrant three. In quadrant three, it's a different formula though. It's going to be 180 plus the reference angle will yield the angle that you're looking for. So it's a bit of a different process because here, this theta was your unknown angle that you're working with presently. And here, this theta refers to the reference. That's an important distinction to make. So in quadrant three, let's take, I'm looking here, by the way. Let's take 225. Let's say 225 is the angle that we're working with. So we would have 180 plus theta is equal to 225. And our theta being our reference angle, this is our angle of interest. Theta is going to be equal to 45. So that's the thing that links these two. Whoops, sorry about that. That's the thing that links these two. So we know that sine of 45, if we go back to our unit circle, let's look at these 45 degrees. And we actually see that sine of 45 and cosine of 45 are the same thing. They're both going to be equal to root 2/2. So if we wanted the sine of 225, well, we know that 225 degrees is in quadrant three. So sine and cosine are going to be negative. This is going to be negative root 2/2. And this should be the same thing as cosine of 225 degrees. And if we look here at 225, we draw our angle down. And yep, we see that it corresponds. And finally, in quadrant four, we have this 360 minus theta. Theta here is your unknown. So here it's unknown. In quadrant 4, it's unknown. And in the quadrant 3, it's going to be your reference angle. That's an important distinction to make. I'm not going to go over the example there, but you can try it out on your own, and it will yield the same results as if you were to do it in quadrant 2 and in 3. So, but that's in degrees. In radians, it's actually easier to traverse the unit circle. So to identify which reference angle corresponds to a given radian measure, you just have to look at the denominator. So let's take an example of 7 pi over 4. Actually, no, let me use a different one. 4 pi over 3. I'm going to write out our reference angles in radians. It's going to be 0, pi over 6, pi over 4, pi over 3, and pi over 2. So 4 pi over 3 is going to correspond with pi over 3. And let's look at the characteristics of sine of pi over 3 and cosine of pi over 3. Looking at our unit circle, pi over 3, our x is 1/2. So our cosine of pi over 3 is 1/2. And sine of pi over 3 will be the square root of 3 over 2. So cool, we can use this for any angle with radians. Radians is much easier to identify than degrees, because degrees you need to memorize that quadrant 3 refers to the reference angle, whereas quadrants 2 and 4 refers to the unknown. And you need to remember those little equations, which aren't that hard to memorize, but it's just one extra thing that you need to. Whereas with radians, you look at the denominator and you should be able to easily spot the reference. I have some practice problems here to just further elaborate what we've been working with. So sine of 240. 240 is in Q3. So 240 is going to be equal to 180 plus theta. Remember, in Q3, the theta refers to our reference. So this theta is going to be 60. So now let's look at sine 60. Sine of 60, let's look at our unit circle. The y is the square root of 3 over 2. And 240, we are in Q3, meaning that it's going to be negative. So sine of 240 is going to be negative root 3 over 2. And we look here, sine of 240. Yep, we got it. I'm going to erase this so that it doesn't get cluttered. Now let's look at cosine of 7 pi over 4. So 7 pi over 4, that is in our quadrant 4, Q4. And 7 pi over 4 directly corresponds with pi over 4. And cosine of pi over 4 is equal to the square root of 2 over 2. We can verify this going to our unit circle, 45, or rather pi over 4. Let's stick to radians. And yep, square root of 2 over 2. And so the cosine of 7 pi over 4, we are in the 4th quadrant, meaning that our x is positive, so this should still be the square root of 2 over 2 as such. So let's go to 7 pi over 4. Yep, our x is positive, so that is correct. So I have 2 tangent examples, because tangent can get a bit more tricky. So let's take tangent of 5 pi over 6. So first, let's just look at this 5 pi over 6. This is going to correspond to our pi over 6. And 5 pi over 6 is in our quadrant 2, which means tangent is going to be negative. So tangent of 5 pi over 6 is equal to sine of 5 pi over 6 over cosine of 5 pi over 6. But we want to use our reference angle before we get into the actual math of that. So sine of pi over 6, let's look at our unit circle, pi over 6. Our sine is 1/2. And our cosine of pi over 6 is equal to the square root of 3 over 2. In quadrant 2, sine is negative. Or rather, sine is positive. My apologies. And cosine is negative. So this is going to be equal to 1/2 over negative root 3 over 2. Let's erase this to make some space. And let's just simplify this out. We're going to multiply by the reciprocal instead of dividing. Negative 2 over root 3. These 2's cancel out. And we have negative 1 over the square root of 3. And I'm just going to rewrite that as negative root 3 over 3, as we have done in the previous parts. I want to elaborate on that further, and that is our answer. And now let's look at tangent of 300. This should be in degrees. I apologize for that. So 300 degrees. We are in quadrant 4. Tangent is going to be negative. That is important. So tan of 300 degrees is equal to sine of 300 degrees over cosine of 300 degrees. In quadrant 4, sine is our negative and cosine is our positive. So now we have to use our little trick. If we know that we are in quadrant 4, we can go back and look at this table and use the 360 minus theta, where theta is our unknown. So 360 minus 300 is equal to 60. So 60 degrees is going to be our reference angle that we use. So sine of 60 degrees, we can look at our unit circle if we're unsure of the value. Sine of 60 is going to be the square root of 3 over 2. And cosine of 60 degrees is going to be equal to 1/2. Now, sine is negative, so we're going to have negative root 3 over 2 divided by 1/2. Cosine of 300 is positive, so the value won't change. And now we can go ahead with simplifying. We're going to multiply by that reciprocal, so negative root 3 over 2 times 2. Cancel out the 2's, we get negative root 3. So the process of going through tangent is much more involved than sine or cosine, but it is equally as important, and we will see how in a few seconds. So now I want to transition into actually graphing the values of sine, cosine, and tangent. With the information we've went over in this video thus far, we can derive the exact values of sine, cosine, and tangent with any given angle as long as we directly relate it to our reference angle. So that's what I've done here in this slide. We have the values of the sine function. I went through, and for every value of x, which is in radians, it's our degree, we have a corresponding value for sine of x. I will not go through the process of proving all of these for their accuracy, as I have already done that, but you can certainly do that, as it is good practice with trigonometry. So now we have this empty graph of sine right here. And here is where we're going to actually go through the graph of sine of x. And you'll notice that on the x-axis, you only see 2 pi, negative 3 pi over 2, negative pi over 2. We don't really see any pi over 4s. We don't see pi over 6. And I only have the quadrantal angles here, which is only the angles on the unit circle which form a right angle. So these guys only. That's why you don't see it there. That's just to simplify the graph, because with the graphs of sine of x, cosine of x, and tangent of x, you really just need to know the shape. That's the most important part. So at 0, sine is 0. I'm going to do this in a different color so it really pops. When x is 0, when our angle is 0, sine is 0. At pi over 2, sine is 1. I guess I should label this right now. We're going to have this as 1 and this as -1. At pi, sine of pi is 0. And at 3 pi over 2, sine of x is going to be -1. Oh, I actually drew that a little further down. So let me be consistent with my scaling. We're going to be right here. And sine of 2 pi is also 0. And now we're just going to work backward. If sine of pi over 2 was 1, then sine of negative pi over 2 is going to be -1. And it's the same process. If sine of pi is 0, then sine of negative pi is also 0. We're negating 0, which is still going to be 0. That won't change. Sine of -3 pi over 2 is going to be 1 if sine of 3 pi over 2 was -1. And sine of -2 pi is also going to be 0. And I'm going to try my best to connect this, but forgive me if it doesn't come out great. Yeah, that didn't come out the best. It's a little wobbly, but you get the point. It's a wave function, and some characteristics of the sine function is that the max value it will ever reach is 1, and the minimum value is -1. It will never go past those two. And that makes sense because on the unit circle, the radius is 1. So you will never go past 1. And the graph of sine of x should look like a wave. It looks more like this if I were to draw it with a more steady hand. So I do apologize about that. This is an iconic graph in math and one that you should get to recognizing. Another iconic graph is the cosine graph. So we have the values of the cosine function here. Again, you can go through the process of proving that these are the exact values of cosine. I will not go over it here for time purposes. I feel like this video is already getting too long. So we're just going to go on with graphing cosine of x. I'll do this in a different color. I'll do it in green. So cosine of 0 is 1. Let's label our axes first. This is going to be 1, and then this is going to be -1. I labeled them 1 and -1 again, and you may be able to see why. So cosine of 0 is 1. I'm going to label that there. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is 1. And I'm going to go through the same process that I did with the sine graph and just negate everything. If cosine of pi over 2 is 0, then cosine of negative pi over 2 is also going to be 0 because the negation of 0 is still 0. If cosine of pi, well, actually, there's something I failed to mention about the cosine graph. It's actually just going to be a mirror image. And we can back this up with looking at our unit circle right here. You can see that with our x values, I'm going to label it with a highlighter. We have positive, 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 negative, 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 positive, 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 negative, negative, negative. It is completely mirrored here along the x-axis of our unit circle. So it should hold to reason that it would be the same on the graph. Cosine of negative pi is going to be equal to -1. Cosine of -3 pi over 2 is going to be 0. And cosine of -2 pi is, well, that is a wonky circle. And cosine of -2 pi is going to be equal to 1. Again, we see the same symmetry over the x-axis, or y-axis, my apologies. And again, I apologize for this little wonky line, but this is the graph of y equals cosine of x. And this pattern, this wave pattern, will continue on forever. It should look something like this. Now we can move on to our graphs of tangent of x. So again, we have the values of the tangent function here. You can go through the process of proving them yourself if you would like. This is a lot more tedious, though, I will say, so do it at your own risk. I do have two rows highlighted, though. We have pi over 2 and 3 pi over 2, and we see that tangent of x is undefined, and I actually do want to notice the pattern at those points. I'll actually only focus on tangent of pi over 2 because it's the same story for 3 pi over 2. So tangent of pi over 2 is equal to sine of pi over 2 over cosine of pi over 2. And we should know these values by now, but I want to use these graphs that we just drew in order to come to this conclusion. So let's go to our sine graph. At pi over 2, sine is 1. This is 1 over, at cosine of pi over 2, it's 0. So 1 over 0. When we divide any number by 0, that is trouble. That is going to land us in undefined, and we're going to see how that corresponds in our tangent graph. We're going to see what that looks like graphically, because it is an interesting phenomena of the tangent function that only relates to it, and it looks radically different to both the sine and cosine graphs, which both take on a wave-like pattern and look very similar. Tangent will look radically different than those two graphs. So I'm going to go here. Tangent of 0 is 0. Let's graph this in blue. Tangent of 0 is 0. Let's go back to this graph. I do not have my tangent graph memorized as I do sine and cosine, as it is much harder to memorize tangent, so I do apologize for going back and forth. So at pi over 2, at pi over 2, it is undefined. So we're just going to label this with some dotted lines. Then at pi, we're at 0. And at 3 pi over 2, we're also undefined. And then at 2 pi, we're at 0 again. And we're always going to have this undefined at intervals of pi over 2. So at negative pi over 2, there's also going to be this dotted line here that signifies our undefined. And same thing with 3 pi over 2. And at negative pi, we're at 0. And at negative 2 pi, we're also at 0. And I think in this case specifically, it is worth having our pi over 4. So I'm just going to write in negative pi over 4, negative 3 pi over 4, negative 5 pi over 4, and our negative 7 pi over 4. And I'm just going to do this for the positives too. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now these I know even less, so bear with me. So at pi over 4, we are at 1. We'll just have 2 units up b1 like we did last time. And at negative pi over 4, we're going to be at negative 1. And if I am not mistaken, it should continue this pattern like this. Yeah, this looks right. We're going to have a negative 3 pi over 4, we're at 1. Negative 5 pi over 4, we're at negative 1. And here, we're at 1. And at 7 pi over 4, we're at negative 1. I'm going to erase these pi over 4s now so that you get a better sense of the graph so that it's not as messy. And when a function is undefined. That means we're going to have a vertical asymptote present. That means it's going to shoot up infinitely in the positive infinite direction or the negative infinite direction. It will shoot up, but it will never touch the value at the dotted lines, our intervals of pi over 2. So it's going to look something like this. We're going to shoot up. It's going to shoot up. It's going to be infinitely large, but it will never touch negative 3 pi over 2. It will never cross that line. And then we're going to come back up. We're going to hit the 3 points, and we're going to repeat that process again. Here, it's going to shoot down to negative infinity. Down here, it's going to shoot to negative infinity. And up here, it's going to shoot to positive infinity, never crossing these boundaries that we've established. We're going to do this process again. We're going to have the negative asymptote, going to hit the 3 points, and we're going to go up again. One more time here. Going to hit the 3 points, and we're going to go up. I could have drawn that line better. Let's do that again. Negative, hit the 3 points, and go up. I'm going to start negative. We're going to hit the 2 points here, and we're going to go up again. We could also draw it down here like this. And this pattern of infinite asymptotes is going to exist for an infinite stretch of time because the cosine graph and the sine graph exists for an infinite stretch of time. And it's really this cosine graph that's giving us trouble. Whenever cosine of x is 0, we have this infinite asymptote. And since the cosine graph stretches for infinity, this tangent graph will also stretch on for infinity. So I thank you guys very much for joining me on this series for the unit circle. I know that it's been long and maybe confusing at times, but I really do think that with some practice, you guys will get a firm grip on it. Knowing these graphs are really important, and this is really why I started this series with the unit circle, so that we can get a good grasp on the sine, cosine, and tangent graphs, because they really do play such a pivotal role in higher math. And so I really hope you guys took something out of this series, and I thank you for your time.